Welcome to lecture series on data structures and particularly linked list. Till now we have seen creation of a linked list, insertion of a linked list, then printing a linked list and counting number of nodes. Various operations we have seen. Now one of the operations, that is deletion. How deletion can take place in singly linked list. So in deletion, what we are going to cover today, I'll explain first general cases, that is how to delete at beginning, how to delete the last node, or how to delete any given node. Then we'll go with the algorithm or what we have to think, and then I'll implement functions for all these three cases. So first of all, we will say deletion at beginning. Means first node we want to delete. What is general case? I'll tell you. Suppose linked list is given. This is linked list. And this is suppose first node or head node. You can call this first or head. In textbooks you might have seen head as a first node's address. Now at beginning means first node you want to delete. So see, whenever you are deleting, keep this in mind always. For deletion, insertion case we have seen. For insertion case, you should have predecessor node's address, that is must. Then only you can insert. For deletion also same thing. Predecessor node's address you should know for deletion. So predecessor should be known. This is, you have to get predecessor, whichever node you are deleting except the first node. If you are deleting at beginning, there is no need of predecessor because there won't be any predecessor. Then for deletion, you have to adjust one pointer. In any deletion case, you have to adjust one pointer adjusted. And whatever you are deleting node, you have to use free function. We have seen in dynamic memory allocation, deallocation. This is one of the deallocation functions defined in stdlib.h. malloc we have used. malloc free, they are defined in stdlib.h, and that you have to include. So free does return the memory whatever you have allocated for a node to free pool. So these things you should know for all deletion also. For insertion, predecessor is required. For deletion also, predecessor is required. For insertion in singly linked list, two pointers will be adjusted. For deletion, only one pointer is adjusted. Then there for allocating memory we have used malloc function, and here for whatever you have allocated for freeing that memory we will use free, which is defined in stdlib.h. How to delete first node. See, when you are deleting first node, if you are deleting this node, the next node will be the first node. That's it. You have to move this first. We have to move this first. Means what? First should point here. Where is this node's address? In first link. So if you say first is given first link, first is given first link, that's it. Only one pointer is adjusted. This is first now. But before that, you should know this node's address for free. You have seen free. Free is a function. Now, which memory you are freeing? Which pointer is pointing to that memory that we have to give? So before movement, store this in some pointer variable. Store first PTR in this, first in PTR, then first is moved, and then free PTR you have to do. Free PTR means what? The memory pointed by PTR. Which memory is pointed by PTR? This memory is pointed by PTR. That we are returning back. So this requires one parameter for free required is pointer to that memory block, whatever you have given. So this is simple case, very simple. This will be done as first node you are deleting. This time required is big of 1, that is constant amount of time is required. See, whenever traversing is not required, then you can say that is big of 1, that means constant amount of time is required. Whenever traversing is required, then that will be big of n definitely. So this pointer adjustments we have to do for deletion at the beginning. Now what special cases we have to check in this? When you are writing a function for deletion at beginning, if linked list is empty, what to do? Can you delete a node from empty linked list? No, right? So we can say that if first is null, then we cannot delete. Moreover, if only one node is available in linked list, only one node is available in linked list, what is condition for one node? One node condition is when first link field is itself null. First is pointing to this node. This is first node. There is no other nodes. Means only one node is present. So what is condition for first node? Only one node. When first link field is equal to null. So what steps we have to take a deletion at beginning? See. First you should check whether linked list is empty. When you say what is condition for linked list empty? When first is equal to null, then what we can say? That is linked list deletion is not possible. Deletion is not possible. Return from this. Not possible. Whatever printf statement, whatever you want to write, and then you are returning from this particular function. When it has only one node. Only one node. What is condition for one node? If first link field, if it is equal to null. First link field null means there is only one node. Now only one node it has, linked list has, and you are deleting that also. Then what happens? When you delete this, linked list will be empty. Means first should be assigned null value. First should be assigned null value. So if this is the case, what we have to do? First is assigned null. That's it. Now for freeing the node, we will see what exactly we have to do. We can see first free that node, and then we can write this. Okay, we will write that also. What we are doing? Free memory for that allocated for first. Now what will happen? This memory, whatever allocated, that will be returned. But first pointer is there. That first pointer we are giving null value. That's it. We have adjusted. If only one node, that node we are deleting, and that first will be null because empty list. After deletion of this, it will be empty list. Now we have checked empty list. We have checked one node condition. This forms the special cases. Now if linked list has more than one node, same whatever link adjustment. If this is not the case, else for this, if I write else, you can write all these in else if also, no problem. So else means what? Linked list has more than one nodes. When more than one nodes you have, directly you can first move this, but before that one pointer should be saved because you require that for freeing. So what else we will do, one PTR pointer will take, and that is given first. So PTR is pointing to this node now. Then what? Now you can move this first. How to move first? First is given first link field. That will move the first to point to next node. Now first is pointing here. Now you have to free this memory, whatever pointed by PTR. So free PTR. That's it. You are done with this deletion at beginning. Now if I want to convert this to function, now whenever you are writing functions, whether you are considering the first node's address as a global variable or local variable, that your everything changes. So what should be signature here for this? As if I assume first node's address as local variable. Some examples we have seen when first was global and what to do. If this it is considered to be local variable defined in main, suppose, then what exactly we can do? How can we write function, that we will see. So if I am considering first as local to main, so what way you can do? What will be signature now? Now see, whenever you are deleting first node, this first node is changing. You are writing a function. You are calling somebody that delete beginning node or first node. Now whenever first node is deleted, linked list you are passing to him. That is first node's address you are passing. But he has to change first node's address. Whatever change he is making, that should be reflected back. So my signature will be struct node star, because first that function is changing. Delete beginning node or first node, whatever you want to give, you can give function name. Now what else you have to pass? The linked list from which you are deleting. So struct node star, I'll take as start as formal parameter. Then whatever we have written logic, that all you have to write here. What we have checked, if that start, whatever you are sending, is null. Similarly, if start itself is equal to null, there is no need of declaring start here. Why? Because this is formal parameter. Formal parameter acts as local variable to this function. If null, what we'll do? We'll say printf empty list, deletion not possible. This will be writing, and then we will return from this. From here only, deletion is not possible. Then what condition we are checking? If this is not the case, it will return from here itself. If linked list is empty, if only one node is present, start link, if it is equal to null, means only one node, then what? It will one node present, so that after deletion of that node, linked list will be empty. So start, we have to, this delete beginning is setting to null, and that should be reflected back, so that we will return that. So after this we will return start. So start is set to null. But before that, as I said, when start is being set as null, you have to free the memory pointed by start. If start is given null, then you have change. You cannot free that. You cannot free that node. So what you can do here, you can write here directly free memory pointed by start. So that memory whatever will be free to free pool, and then you can set start as null. So this is done. Else part for this. What will be else part now? Else, if this is not the case, what we store this node's address. What ptr is given start. Why we are doing this? Because we need to free that. Then this start is moved. What start is moved. Start is given starts link. You have moved this. Now start is pointing to next node. That's it. Start has been set here. And then you can say free this ptr. Free ptr. Now as a last statement after this, what you have to return this wherever start is pointing, that when it comes out of this block, finally you can write return start. So this will be returned back. So these things we are doing in deletion of the first node. Now we are using ptr. See, start we are using start is a variable accessible in scope because formal parameter acts as local to this. We can access that, but we are using here ptr. ptr is not a temporary variable. We have not declared. So here you have to declare struct node star ptr. Now see whether it works for every cases or not, we have to check. See, whenever this function is called, we are sending first to this function. That address start will come here. So start is also pointing to this whatever linked list created already. When control comes here, one pointer variable is created. Whether start is null, not null. If it would have been null, then it would say empty linked list. From here itself it will return, but it is not empty. But it will not go into this block, it will come out of this block directly to here. Start link is equal to null. Is it start link null? No. Means this list whatever passed has more than one nodes. Control comes to else part. Then ptr is given to start. This ptr is given to start. Then start link, start is moved. Start will point to this node. Then free pointer, this is freed. The memory which is pointed by pointer is free. Then return that start. So this starting address we are returning back. This is all about your. See, we can write in different ways also. See, it depends on what exactly we are doing, how pointers we are adjusting. This I am considering start node as this local variable. We'll see pointer adjustments for deletion of the last node. Deletion of last node. I will consider this list. This is end, suppose. And I want to apply deletion of a last node. Which is last node? This I want to delete. When I am deleting this node, then what will be successor for this? There won't be any successor. So this field we have to make it null, right? Now when you have to make this null, this field, you should know this node's address. So for deletion of this node, predecessor node is required. Predecessor node's address is required, then only you can access this field. So I have to traverse so that I can put a pointer to predecessor node. I have to find out this predecessor. I'll take as temp, suppose I am checking, and I have to stop somewhere here. Then only one pointer adjustment I have to do here in this case. Now I'll free this memory first. What I can write here? Free temps link, because that node, what is address of the node we are freeing? Temps link is pointing this node. This memory we are freeing. You free that and set this temps link. What should be temps link field? Temps link field will be null. That's it. This will become null. So the major task in this is to locate predecessor node. And if you can locate predecessor node, then that's it. In earlier lecture, in earlier one video, I have shown you, I have given two ways for locating predecessor. One is by using only one pointer, and the other is with two pointers we have seen. Now see, I'll explain what. This is a general how pointer adjustment we have to do. One pointer you have to adjust for deletion cases. Now how to locate this last but one node? Now tell me, what is property of last but one node? What is property of last but one node? If you see, the next node's link field will be null. Pointer is here, next node's link field is null. When you are getting this, what is address of this node? Temps link. How to access this particular field? This is link field. This node's address is temp link, because temp is here. This address of this node is temps link. This node's link field, how to access? Temp links link field. Now you are keeping temp here and you are accessing this. If that is null, that means you have reached to the last but one node, that we can say. So this way, keeping temp here, you should check next node's link field. Next node's link field. So what will be the scenario or algorithm for this? We'll see. For getting predecessor node, as traversing is required, point first to first node. So we will take temp is given first node's address. Okay, I have to repeat something. When I want to stop last but one node, so temp, keeping here temp here, you are checking this link field. So temp links link. If it is not null, this is not null now, means this is not last but one node. So you have to move. When you are moving, see, temp will be here. Keeping temp here, you are checking this field. Not null, this field is not null, move. Keeping temp here, you are checking this. Now it is null, we are stopping movement here. So when we are moving while temps link, when it is not equal to null, then we are moving temporary. Temporary is given temps link field. That's it. When you write this, then it will locate your last but one node. Last but one node's address. What will happen? See, you have nodes. First is pointing to temp, yes. Temp links link. Temp link pointing to this node. Its link field. This. Is it null? No. When no, not null. When no, this is true. Temp is moved. Temp is moved. Temp will point here. Then again it will come to while loop. Temp links link. Temp links link. This node's link field. It is not null. Temp is moved. Temp will point here. Then temp's link. Temp link means this node. This node's link field. This link field is null now. When null, this condition is false. When condition is false, temp will stop there and you are located the last node. That's it. Temp is pointing to last node after this loop. Now what steps we have to do after this? You can free that nodes, whatever memory you have allocated. How to do that? Temp's link. You are freeing the memory given to this node. This node's address is temp link. So you are freeing that. Then what? Temp has to, this temp's link field has to be null. So temp's link field has to be made null. That's it. This is central logic. Now you should see whether this logic works. Now what you have to check before this? If linked list is empty, can you delete last node? No. So whatever we have written in the first previous program, you have to check whether empty linked list. If empty, deletion not possible, return. If only one node is present, whether this logic is useful? No. When one node is present, you are changing first and you are returning that there itself. Same, that both cases, whatever earlier we have written, that will be same in this case also. Only if it has more than one nodes, then this is logic. So what you have to do while writing the function for this deletion of last node, the first two conditions whatever we have checked, that will be similar to deletion of from beginning. Then you have to do these steps. If it has more than one nodes, this will check whether it works for two nodes only. Two nodes. This is two node condition. I mean two nodes, first two condition will be false. Then we come to else part. First is given temp. Temp will point here, right? Now temp's links link. Temp link is pointing to this node. Its link. Link is null. It is null. This condition is false. When false, it will come out of this loop. It will come here. See, you should know when I am not giving curly brace set, only one statement is assumed to be in that control structure. When curly brace set, beginning of curly brace, ending curly brace is not given, one statement is assumed to be in this particular control structure, anything. So, control comes out, free temp's link. Temp's link is this node's address. This node will be sent to free pool. Then it can be reused later. Then temp's link, temp is pointing here, temp's link is given null value, means there is no node after this. So this is deletion. Only in earlier function, only if you add this, then it is sufficient in place. This locates the predecessor of last node, means last but one node. Temp will be pointed to that last but one node, and your link adjustment, only one link has to be adjusted. That's it. So this is, I won't write now delete at end. Same program, similar way also you can write.